Within the high-tech industrial corridors of mainland China, a fundamental shift in energy production is quietly taking place as engineers begin to scale a new generation of solar panels that are nearly twice as capable as the standard installations found on modern rooftops. Despite occupying the same physical footprint and utilizing the same amount of sunlight, these advanced modules are generating almost double the electrical output. The catalyst for this sudden leap in efficiency is not an exotic laboratory invention from the future, but rather a mineralogical curiosity first identified in the Russian mountains nearly 2 centuries ago. For almost 200 years, this material remained an obscure entry in geology journals until a pivotal experiment in Japan in 2009 revealed its extraordinary physical properties. For the last 7 decades, the global solar industry has been tethered to a single dominant material, silicon. This element must be processed at temperatures exceeding 3,000 degrees Fahrenheit and sliced into wafers thinner than a human hair to function. While silicon has been the undisputed engine of the renewable transition, it is now approaching a definitive physical bottleneck where further improvements are becoming increasingly difficult to achieve. The new crystalline alternative currently breaking world efficiency records does not suffer from these limitations, and it is already moving through production lines capable of turning out millions of units annually. By the end of this analysis, you will understand how a mineral that was once considered a geological footnote is now poised to make traditional silicon solar panels obsolete within the coming decade. To understand why this change is necessary, we must first look at the invisible wall that silicon cannot scale. Silicon has rightfully earned its status as the foundational architecture of the modern solar world. It is the characteristic blue-black material found inside almost every photovoltaic cell in operation today, whether it is powering a residential home in the Arizona desert or a massive utility-scale farm in Inner Mongolia. Silicon is remarkably resilient, capable of surviving on a rooftop for 25 years with minimal maintenance. However, silicon possesses a hard physical limit that is dictated by the laws of thermodynamics rather than a lack of engineering talent. Regardless of how perfectly a silicon solar cell is constructed, it can never theoretically convert more than approximately 33% of the sunlight hitting it into usable electricity. In the commercial market, current high-end panels operate significantly below that ceiling, typically converting between 20 and 22.5% of solar energy into power. This means that roughly 80% of the solar radiation reaching a standard roof is effectively wasted, either bouncing off the surface or dissipating as heat. For several decades, the industry relied on marginal efficiency gains, often celebrating improvements measured in mere fractions of a percent. But by the early 2020s, these incremental improvements became harder to achieve and even more difficult to economically justify. As one senior industry executive noted, in 2025, silicon has reached a point where almost all its potential has been exhausted. There is a small margin left for improvement, but the cost of capturing it is steep. Furthermore, the manufacturing process for silicon carries its own heavy industrial and environmental burden. Converting raw quartz sand into high-purity silicon crystals requires enormous amounts of electricity to sustain furnaces that operate past 3,000 degrees. The industry found itself in a stalemate. The very material that enabled the clean energy revolution was now running out of room to grow. The breakthrough eventually emerged from a mineral that had been sitting on laboratory shelves for nearly 2 centuries. In 1839, a mineralogist exploring Russia's Ural Mountains identified a new crystalline structure that was eventually named Perovskite. For over 150 years, it remained exactly what its name implies, a rock. While geologists studied its structure, no one in the energy sector considered it a viable candidate for power generation. However, the physical rock itself is not what matters to modern engineers. What matters is the specific atomic lattice, a unique and repeating structural pattern. Scientists eventually realized they could synthesize entirely new materials that mimicked this pattern using inexpensive and abundant chemical precursors. These lab-grown crystals share the structural DNA of the original mineral, but are engineered specifically for the task of harvesting sunlight and converting it into electrical current. In 2009, a Japanese researcher named Tsutomu Miyasaka attempted to construct a solar cell using this material for the first time. That initial prototype was extremely primitive by modern standards, converting less than 4% of sunlight into electricity, making it less efficient than silicon technology built decades earlier. Yet, the material exhibited a unique physical advantage. This crystalline structure absorbs light approximately 10 times more aggressively than silicon does. This means a layer of the material just a few hundred nanometers thick, which is thinner than a soap bubble, can absorb as much solar energy as a silicon layer, hundreds of times more massive. Unlike silicon, which requires energy-intensive furnaces to grow perfect crystals, this new material can be dissolved into a liquid ink and simply coated onto a surface at room temperature. Researchers watched as the efficiency of this new technology climbed faster than almost any other material in the history of photovoltaics. Within a mere 15 years, laboratory-grade cells were matching and then surpassing the performance of the most advanced silicon cells ever manufactured. By 2026, a privately developed Chinese cell achieved an efficiency rating of nearly 28% under standard sunlight conditions, officially breaking the world record for single-layer cells. A technology that began at less than 4% efficiency had in less than 2 decades overtaken a rival that the world had spent 70 years perfecting. If this material is truly as promising as the data suggests, the obvious question is why every rooftop is not already covered in it. To understand the delay, we have to examine the reputation this technology earned during its early development, which caused many serious engineers to remain hesitant for years. The initial iterations of these cells suffered from a severe stability crisis. While they were brilliant under controlled laboratory conditions, they were often prone to rapid degradation in the real world. Exposing an early sample to moderate humidity could cause the crystalline structure to break down within days, and prolonged heat exposure would cause its performance to quietly fade. Even ordinary sunlight itself, specifically the ultraviolet spectrum, could slowly erode the material's integrity over time. Within the industry, it was often dismissed as a lab queen, a technology that was dazzling in a sterilized environment but incapable of surviving the rigors of an outdoor installation. There was also the significant challenge of chemical safety. The most efficient versions of these crystals rely on a small amount of lead, a toxic heavy metal, to stabilize the lattice structure. While the actual amount used is tiny compared to the soldering found in older generations of electronics, it became a major regulatory and environmental concern, particularly in regions with stringent safety mandates like the European Union. Overshadowing all of these concerns was the massive question of long-term durability. Silicon panels are routinely backed by 25-year warranties because manufacturers possess decades of empirical data proving their longevity. By contrast, early versions of this new crystalline technology could lose significant performance in just a few months. No utility company, homeowner, or institutional bank is interested in financing a solar project that might not survive 10 years, let alone the industry standard of 25. Because of these factors, the technology spent a decade as an impressive academic discovery that was always considered 5 years away from being ready. Then, the industrial approach underwent a massive tactical shift. Engineers stopped asking how to make this new material replace silicon entirely, and instead began asking how it could enhance it. This shift in perspective changed everything for the global energy sector. Instead of treating the two materials as rivals, engineers began stacking a thin film of the new crystal directly on top of a standard silicon cell. This dual-layer architecture is known as a tandem cell, where two different materials function as a single integrated unit. Sunlight contains a wide spectrum of colors and energy levels, and a single material is naturally limited in how much of that spectrum it can capture. The top layer of the new crystal is specifically tuned to absorb high-energy blue and green light, while the silicon layer sitting underneath is naturally optimized to harvest the lower-energy red and infrared light that would normally pass through a standard panel untouched. Sunlight hits the upper layer first, where a significant portion of its energy is absorbed, and whatever remains continues down into the silicon foundation, which mops up the rest. The result is a single integrated panel that harvests a much broader range of solar energy than either material could ever manage on its own. Because it captures more of the light spectrum, the theoretical ceiling for efficiency climbs well past the old silicon limit, with researchers now targeting a maximum potential of over 45%. The side-by-side comparison reveals the massive scale of this advantage. A standard silicon panel converts roughly 20% of sunlight and produces between 400 and 500 watts of output. A tandem panel using this exact same physical footprint has already demonstrated 29.2% efficiency and over 900 watts of output. This represents nearly a doubling of power density on the exact same amount of roof space. While these results were once confined to elite research facilities, the focus has now shifted to industrial scaling. The technology is no longer sitting in pilot labs waiting for funding. It is already being deployed at an industrial scale, and the manufacturing data behind this transition is arguably more important than the efficiency records themselves. The biggest industrial advantage of this new crystalline coating is that it can be applied using a high-speed printing or coating process, similar to how newspapers move through a press. This is a massive departure from the slow and energy-hungry furnace cycles required by traditional silicon. Once you attempt to build millions of panels per year, this difference in manufacturing speed and energy consumption becomes a decisive competitive edge. China moved with extraordinary velocity to secure this advantage. By 2023, Chinese manufacturers had already achieved meaningful production levels, and by the mid-2020s, they had pushed into full industrial-scale manufacturing. Several factories are now capable of producing enough panels annually to power hundreds of thousands of homes, with even larger facilities currently under construction. These projects are no longer just demonstration sites. They are significant industrial commitments backed by major capital investments. The environmental math also supports this transition, as the room temperature coating process generates approximately 30% less carbon dioxide per watt of capacity than the traditional smelting process. A technology that is cheaper to manufacture is also proving to be significantly cleaner to build. This strategic backing was elevated to a national priority as far back as 2021, and that coordination has allowed researchers to move laboratory breakthroughs into commercial products in under 2 years, a pace that has significantly widened the gap between international competitors. The transition from a record-breaking laboratory result to a panel that can survive 25 years on a residential rooftop represents the most significant hurdle currently facing this new industrial sector. While the headlines often focus on the staggering efficiency gains, the part of the story that is frequently overlooked is the monumental task of manufacturing at scale. Having a world-class solar cell in a controlled environment means very little if a manufacturer cannot produce it by the millions with consistent quality. This is where the narrative shifts from pure physics to the complex math of industrial engineering. The primary manufacturing advantage of this crystalline coating is its ability to be applied through a high-speed printing or coating process. This method is similar in principle to a commercial printing press, representing a radical departure from the slow, energy-heavy furnace cycles required to produce traditional silicon wafers. This fundamental difference in production speed becomes a massive competitive advantage once the goal is to build millions of units annually. The pace of industrial deployment in East Asia has been extraordinary, with several major manufacturers moving past demonstration projects and into full-scale industrial commitments as early as 2023. By the middle of this decade, the infrastructure for high-volume production has matured to a point where some factories are already capable of powering hundreds of thousands of homes with their annual output. These facilities are backed by significant capital investments and a coordinated national strategy that has been in place since 2021. This level of institutional support has allowed researchers to move laboratory breakthroughs onto the factory floor in under 2 years, a process that typically takes up to 5 years in markets without the same level of centralized coordination. The environmental implications of this manufacturing shift are also becoming a key part of the conversation. Data from earlier production lines suggests that this new room temperature coating process generates approximately 1/3 less carbon dioxide per watt of capacity than the traditional smelting process. In a market increasingly focused on carbon footprints, a technology that is both more powerful and cleaner to build represents a formidable threat to the status quo. Despite these industrial advancements, the question of long-term durability continues to tower over the industry. Traditional silicon panels are frequently sold with 25-year warranties because the sector has decades of empirical data from real-world installations to back up those claims. The new tandem architecture, while promising, simply does not have 25 years of real-world proof yet. This creates a significant gap between what is possible in a lab and what is bankable in the real world. Serious engineers and institutional lenders are famously risk-averse, and they require more than just accelerated stress tests to commit billions of dollars to a new technology. While recent laboratory results are highly encouraging, with newer versions maintaining over 98% of their performance after thousands of hours of intense heat and humidity testing, the industry knows that a lab simulation is not a perfect substitute for 2 decades of real-world winters and heat waves. This brings us to the concept of bankability, which is perhaps the most important metric for the future of large-scale solar farms. A utility-scale energy project is a massive, long-term investment, and banks are reluctant to finance projects based on unproven hardware. Even a panel that produces double the energy of its predecessor may struggle to find financing if there is even a small margin of uncertainty regarding its performance 10 years down the line. Most industry analysts anticipate that these high-output panels will not become the fully trusted standard for large-scale bank-financed projects until somewhere between 2027 and 2029, once a few more years of real-world rooftop data can be analyzed. There is also the persistent challenge of environmental safety, specifically concerning the lead content within the most efficient crystalline structures. While the quantity involved is minimal, it remains a focal point for regulators, particularly within the European Union. To address this, manufacturers are developing sophisticated encapsulation techniques designed to ensure that the internal materials remain completely isolated from the environment, even if a panel is physically damaged. At the same time, researchers are exploring lead-free alternatives to ensure the technology can meet the strictest global environmental standards in the future. These are not seen as insurmountable obstacles, but rather as necessary engineering milestones that must be cleared as the technology moves toward a ubiquitous presence on the global market. What is perhaps most striking about this transition is that it is not necessarily a story of one material completely dethroning another. Instead, it is a story of unique industrial synergy. The dual-layer design that is currently winning the efficiency race depends entirely on the silicon layer underneath being there. In this sense, silicon is not being made obsolete. It is being given a massive technological upgrade. This partnership allows the industry to leverage the massive existing infrastructure of silicon manufacturing while breaking through the efficiency barriers that have stood for nearly 70 years. It is a technological evolution that breathes new life into a mature industry, pushing its boundaries well past what was previously thought to be a hard physical limit. The distance between an impressive research paper and the panel bolted to a residential roof is closing at a velocity that few predicted even 5 years ago. We are moving from an era of incremental gains into an era of fundamental power density expansion. The focus is no longer just on how many panels can be installed, but on how much energy each square foot of those panels can actually harvest. For the first time in the modern era, the ceiling for solar efficiency is moving toward 40% and beyond, which would have sounded like pure science fiction only a decade ago. The implications for land use, grid stability, and the overall cost of renewable energy are profound. The narrative of solar power is shifting from a story about a single, reliable crystal to a story about complex, high-performance molecular engineering. The geological discovery from the 19th century has finally found its purpose in the 21st, serving as the catalyst for an industrial shift that is already well underway. As the manufacturing math continues to improve and the durability data accumulates, the transition appears increasingly inevitable. The industry is moving toward a future where every single panel is fundamentally better at its core job, capturing more of the solar spectrum than was ever thought possible. This is the front line of the new energy economy, an industrial race that is being decided right now in the factories and laboratories that are defining the next generation of global power. The 1839 discovery from the Ural Mountains has quietly rewritten the rules of the energy transition, proving that sometimes the answer to the future's biggest problems has been sitting right in front of us for nearly 200 years.